this presentation is going to be in English, even though I am from here, but I don't know any of the knowledge in Russian. So but feel free to ask questions in Russian. Interrupt, whatever. So my name is Stoyanovich, and I'm a postdoctoral researcher at the University of Pennsylvania. I got my PhD at Columbia University in New York 2 years ago. And my research is in data management. So I was one of the lecturers at the RAS IR/EDBT summer school, and I am from the EDBT part. So EDBT is the extended database technology. And I think the main difference sort of between IR and DB is that we try to go more top-down. We try to sort of, model maybe simpler problems and then see how they would apply in the general context. So really the difference gets blurred more and more within the applications. And so I just wanted to give you an overview very quickly of what I work on before I get into the particular topic of today. And my work is in two large sort of areas. One has to do with how one can represent large data sets of complex objects of various kinds. And another has to do with having represented large data sets of complex objects. How do you help the user find what they're looking for in them? And by find, I mean that either you can allow your user to issue a search query, for example, and return ranked results, or you can try to show to the user a kind of an overview of the data set that shows its richness, so that the user can then understand what it is that they're looking for better. And in particular, the work that I will talk about today is rank-aware clustering. And it appeared in two recent conferences, in CITM 2009 and in EDBT this year. And this work is sort of very characteristic of the types of approaches that I like to take, because it combines ranking, showing results in order, and also clustering that really presents the richness of the data for the user, allowing them to better understand their information. Am I going too fast? So I'm from New York, and New York accent is a foreign accent. So here you're hearing the typical New York accent. I also like to build applications as prototypes, and I have built several over the course of the last several years. And in particular, the algorithms that I will describe to you today were implemented in scope of the Yahoo Find Love prototype, which was working on top of Yahoo Personals. And this is a very large dating website, a website where people can find other people to date. And I will show you some screenshots of what the Yahoo Find Love look like, and also we'll discuss some results of validation with actual users that we do. I also work a lot with biological data, so if any of you are interested in that kind of data, come and take my card. I can talk about it. So, is this working? Oh, thanks. Let's just this first slide is going to motivate the action problem that I will talk about today. And just to remind you of the title, it's what is that action problem? Making interval-based clustering rank aware. And as I mentioned before I started, the problem that we address here is how you can present to the user data sets in which items are intrinsically incomparable. So it's like data sets that contain apples and oranges and cherries, but the user doesn't actually know what is in that data set. So when we show the data, we want to differentiate between apples and oranges and cherries and then so on. And this is done automatically. So our motivating example here comes from Yahoo Personals, which is a dating website, once more. And consider that there is this dating service user, Mike, who is looking for a date. And Mike tells the system that he wants to find matches who are between 18 and 40 years old, who at least started going to college, and who make more than $50,000 a year. So this is unrealistic probably by Russian standards. It's also not very realistic by US standards. $50,000 a year is not a very high salary, but for somebody who is relatively young and just started college, it's not a very likely outcome. But this actually, this kind of query is something that we found a Yahoo Personals user to have asked. His name was not Mike, I'm not sure his name, but there is a user who actually is expecting to find matches of this kind. And furthermore, in Yahoo Personals, Mike wants to rank his results, to order them. And in this very simple example, Mike is just going to order results by income from higher to lower. So when he gets his results back, and I don't know how well this translates, so you're going to have to help me. Mike gets a very long list of matches. This is because Yahoo Personals in particular, and also many other data sets that are large instructions contain, millions of objects, and all of these thousands may match a user's what we call filtering conditions, that sort of age, education, income brackets that he defined. So there are many results, and in particular, this is problematic because all the results at the top are very similar. So here you can see that the first 999 matches all have the same attributes. They are MBAs, that's Masters of Business Administration. These are people who do work as executives in the financial industry, for example, in the US. I don't know what that degree translates to here. And they tend to make a lot of money compared to others. So all of these people are MBAs. They're 40 years old. So that's the older part of Mike's bracket. He asked for 18 to 40. And they all make $150,000, which is really sort of the maximum that you can specify in Yahoo Personals. It's 150 plus. And this is problematic. This result homogeneity is problematic because it does not allow Mike to explore any other types of results here. Mike did not ask for people who are exactly 40, are MBAs, and make $150,000 a year. He asked for a wider range of people. And he may want to actually find somebody to date who is younger, maybe 25, and maybe makes less than an MBA who's 40, but perhaps their income potential will increase with age. So Mike does want to see a variety of answers, and a ranked list of results is not going to allow him to see this. Right. And so why is this match homogeneity happening? Why is it so that all results, or many results at the top, are so similar in terms of their attributes? Well, in this example, it's pretty obvious. It's because higher age correlates with higher income. The older you get, the more money you make. And also certain types of education correlate with higher income. So here, MBA correlates with higher income. There are also some PhDs or slightly younger, but they make less money than the MBAs. And then there are these much younger matches here who only finished college, have a bachelor's degree, make far less, but as I just argued, they may also be of interest to my client. Because even though they make less money, they're younger. Right? So you buy this example, I hope. So let's look a little bit more into these correlations that happen between item attributes and the ranking function. And we refer to this as rank-aware correlations. So what I'm plotting here, and this is actually from Yahoo Personals, this data, over all the women who have stored profiles in Yahoo Personals as of 2 years ago. I'm plotting on the x-axis the age between 18 and 40 years old. And on the y, I'm plotting the percentage of matches who, with the red line, have an education higher than bachelor's. So either a master's, an MBA, or a PhD. And the blue line says who make more than $50,000 a year. Yahoo Personals is a US data set. So this is all of the United States averages. So what do we see here? We see that, first of all, education and income both increase until the age of 29 roughly. Right? At which point income continues increasing, but percentage of women who have a postgraduate education plateaus, so it no longer goes up. Which means more or less that if you didn't go to graduate school, if you didn't try to obtain a graduate degree until 29, you're not going to. But the older you get, you continue making more money because you gain more experience, because your employer somehow feel that they should pay you more if you're older. So, in particular, as far as correlations, what this means is first that these correlations are unpredictable. I would have known a priori that 2029 is this breaking point where first income and education goes through, and then one continues growing and the other plateau. And another thing that this tells us is that correlations are local. So higher age correlates with higher income over the entire range that I'm plotting here, over the entire 18 to 40. While higher age correlates with higher percentage of women who have a postgraduate education only until the age of 28 or 29. And then it no longer correlates. So what I mean by this locality is that correlations may hold between subsets of attributes and on subsets of their value ranges. Are you with me here? And even income doesn't keep going up, all the way with age. It plateaus at some point when you retire, and then you're on a fixed income. So this is not a given either. So what we're going to want to do is account for this locality of correlation. I don't know what's there. And we will work towards a solution that will allow us to present, rather than presenting a single rank list of results that I showed to you earlier on, presenting multiple groups, clusters of results, where each group represents best matches from among comparable matches with respect to the ranking function. And I will explain to you in the remainder of this talk what I mean by best from among comparable. So these groups, these clusters, are going to be presented to a user, and then when the user clicks on one of them, he or she can see a ranked list of results that have these attributes here, or these attributes, and they will be ranked again according to the ranking function that the user gave. So what we're seeing here is there are still these older, relatively older matches that make more money. But also the user is still able to explore younger results that have a lower education level relatively and make relatively less money than these highest earners. But these are the highest earners from among their respective age group and education level. Right? So this should be intuitive. And notice also that some of these overlap. So each one of these groups, and this is a toy example with just 3 attributes. In reality, in Yahoo persons, there are 30 attributes that you would look for subsets of. In these groups, there might be some matches that are there more than once. For example, this girl on the left here is here and also there. The idea is that the different groups represent different aspects of correlation between attributes and the ranking function. So, for example, somebody could be a high earner because they're relatively older. Somebody else could be a high earner because they are from an advantaged background. They live in New York on the Upper East Side and have rich parents. Whether or not they're older doesn't matter. Right? So these are different aspects of goodness, different aspects of correlation between attributes and the user's ranking function. This is not very responsive. Okay, am I clicking the wrong button? So what I just told you was like a lengthy introduction, and now I will go through 3 little subtopics. First, I will discuss rank-aware clustering, what it is, how we define it, and I will also present an algorithm called BARAC that will allow us to find rank-aware clusters in large structured datasets. Next, I will present results of an experimental evaluation in which I will demonstrate both that BARAC is scalable, that it can find these clusters in a manageable amount of time, and I will also demonstrate to you that these clusters, these results, are considered by users to be effective. That they like the results that they see, and they're able, in our case, to find weights more easily. And then I will conclude. So, the basic framework, clustering framework that I will use here is subspace clustering. Right? What is subspace clustering? It's a way to find clusters in high-dimensional space that accounts for locality. So here's a sort of a pictorial example of this. You have to have a 3-dimensional space, and the points only represent items or objects. And you can see that some of these clusters exist in subsets of the dimensions. So in particular, these green and red cluster, they only exist in dimension C and dimension A. And dimension B is noise for them. Right? Likewise for the other 2 clusters. So here's an actual projection of the original space onto either one-dimensional, what we call subspaces. So we project on dimension A, B, or C. And here there are combinations of 2 dimensions. So we're projecting on 2-dimensional subspaces. The argument for subspace clustering says that in datasets such as the one that I showed to you, there is no one dimension and no combination of 2 dimensions that will allow you to discriminate between all 4 clusters. So depending on which cluster you are in, there is a different set of dimensions that you need to consider to be able to tell that cluster apart from others. this is, for those of you who are familiar with PCA, principal component analysis, is a very different approach. So PCA is this approach that people take in machine learning where they start with a high-dimensional space and they reduce it to a lower dimensional space by just choosing a subset of dimensions that are most discriminative. For example, I start with 30 dimensions, and I choose the 3 best that allow me to tell the clusters apart. Here, in a dataset such as this doesn't work because there are no 3 dimensions, no 2 dimensions, and no 1 dimension that I can choose that would allow me to tell all the clusters apart. So for example, here, if I just project on A, I can tell the red cluster apart from the rest, but the others are more difficult to tell apart, right? So the best really that I can do is to project onto A and B, which will allow me to tell red and green from the rest. And then project on B and C that would allow me to tell the blue and the dark blue from the rest of the clusters. Are you with me, more or less? So this is what we want. We want to find, depending on where we are in the data, we want to find combinations of dimensions of attributes. In our case, that's age, education level, etc., height, shoe size, and value ranges in which these attributes will allow us to tell some clusters apart. And subspace clustering is not something that I came up with or my co-authors. This concept exists. So what we will do is we will provide a way to make subspace clustering rank aware to account for this ranked correlation between attributes. So how would we find subspace clusters where there have been several approaches. Let me just open this up. Right. So first, what we want is to find clusters in multiple possibly overlapping subspaces. In that example that I gave, there were 2 subspaces that were good. One was on A and B, and then the other was on B and C. They overlap in their dimension B. They have that in common. And why do we want this? Apart from wanting to account for locality, well, also having subspace clusters is going to make it easier for the users. Because we can describe subsets of the dataset to them by using just a handful of attributes, just age and education, for example. We don't have to try and describe clusters that are there in the full dimensionality, size 30. So some examples of these clusters are right here. So age 20 to 25, and education bachelor's, and income $25,000 to $50,000 a year. That's a description of a cluster in the subspace of the full data set. There have been two main approaches given for identifying clusters in subspaces, and these are top-down and bottom-up. So top-down, you start with a full dimensionality, and then you kind of remove some dimensions that are maybe not relevant. Don't tell you enough. And another approach is bottom-up, where you start with one-dimensional projections, and then you grow the dimensionality. So first you start with looking for clusters in just age or just education, and then you try to combine them. And an approach that we will use here is bottom-up. This is because bottom-up algorithms have been shown to be more scalable. It's just more efficient to find clusters this way. The complexity is lower and scalability is better. So, given, and hopefully that you believe me, that subspace clustering is the way to go here, what we need to do is define the problem a little bit better. And in particular, we need to discuss what a cluster is to us. How do we define a cluster? For this, we need a measure of quality. And also, we need to figure out how to find these clusters. So that means that we need a search strategy, a way that will help us explore this space. So here's a formal problem statement. And this is the problem that I will address in the remainder. Where given a user specifies a query, Q, and this query is just a conjunction of filtering conditions on one attribute each. So this could be either attribute equals a value, or it could be attribute is in a range of values. Like here, I'm giving you age 20 to 40 and education at least bachelor's. So bachelor's or higher. This is a typical set of filtering conditions that a user would specify in a dataset such as Yahoo, for instance. In addition to this, a user also specifies his preferences, which the system then transforms into a ranking function. So the way that the user specifies preferences in structured datasets is typically by choosing from a menu of available ranking attributes or scoring attributes. So these are attributes in which there is any order. For example, a user may say that he wants to sort results on income, and he also says in what order, from higher to lower. And I denote this like that. And also user wants to maybe rank on age from lower to higher. So what does this say? This says my user prefers higher income and lower age. Doesn't everybody, right? And that's very difficult to attain. And there are some other attributes, ranking attributes in the Yahoo personal dataset in particular. These are height, weight, how often people go to attend religious services, and there are some others. And you can imagine that in other datasets, for example, in a dataset of apartments, some of these ranking attributes might be the price of an apartment, how large it is, what floor it's on. So all of these attributes in which there is an order over the values. Are we okay? So our particular approach to ranking word clustering does not assume any kind of shape of ranking function. I will in my experiments use a particular kind in which a score of an item is just a weighted sum over the ranking attributes. But we do not assume our approach treats this ranking function as a black box. It does not assume any particular kind of a function, what known as unicity. All that we need is that ranking has something to do with the attributes. That there is some correlation between a score of an item and the attributes of that item that the system has information about. So what is the problem that we're trying to address? We're given a query such as this one, and we're given a ranking function. We want to find rank-aware clusters in subspaces of the datasets of the dataset. So what are these rank-aware clusters? They are themselves subspaces that have certain properties, and these properties are they are sufficiently good. They have sufficient rank-aware clustering quality. They are tight and they are maximal. And I will tell you what I mean by all of these things right now. But before I tell you this, I want to give you the general outline of my algorithm. And this is a typical sort of bottom-up subspace clustering algorithm, but it's just going to use different measures of quality and different ways of exploring the spaces because of our different problem formulation. The algorithm is called BARAC, which stands for bottom-up algorithm for rank-aware clustering. I think you can guess my political orientation based on the name of this algorithm. And we started thinking about this just as Obama was getting elected for the first time. So this was our support. So the algorithm has three basic stages, And this is similar again to the rank unaware subspace clustering algorithms that are bottom-up. The first stage is build grid. What happens in this stage is that we split each dimension, for example, age, height, into intervals. And we compute in our case the top n for each one of the intervals. So what do I mean by this? Let's say that our dimension is age. We're going to take all of our data, all of the items, and we will create, let's say, 10 intervals on age. So an interval is going to be something like age 20 to 24, 25 to 30, etc. For each interval, we will take all of the items that have the value of age in that range. So for 20 to 24, we'll take all items that are in that age bracket. We will compute the score for each one of these items. And the score is according to the complete user's ranking function. So it might be a combination of height, age, income, and then anything else. And we will sort all of the items that fall inside that bracket. And we will take the top n and then report it. So for each interval, we will know what are the highest scoring n items. And then is a constant, it's something like 100 or 200. In the next stage, what we will do is we will walk along each attribute, and we will think about whether or not to merge together consecutive intervals along that attribute. I will tell you later on how to make that decision. But basically, sometimes we want to consider these ranges separately. 20 to 24 is different enough for us, and it's promising, than 25 to 30. And sometimes we want to put them together. And the final stage, is the join, and this is where we grow the dimensionality of our clusters. So far we were only dealing with one-dimensional intervals. Next we're going to be combining them. So we might, as a result of this stage, build a two-dimensional cluster out of one-dimensional ones, or we might build a three-dimensional cluster out of two-dimensional ones. The properties that I mentioned briefly and that I will drill into right now are taken care of in these two stages. So tightness is a property that will allow us to not to deal with mesh homogeneity and top rank. Is going to be ensured during merge. And the two other properties that we want, maximality and rank-aware clustering quality, are going to be taken care of during the join stage. So let me just give you an intuition for these three properties that we want to ensure. And I won't get into very, very much detail, so this is going to be more or less tutorial. So the first stated goal here is that we don't want to return ranked lists that are very long, but at the top everybody is alike, because then our user gets bored. And furthermore, we don't want to produce a description for such a long list, where the description does not agree with the properties of the top ranking items. So here what I have is that all top ranking items are 40, and then they make $150,000. A description that says age 25 to 40, income 75 to $150,000 does not correctly represent the top end. This is mesh homogeneity. That's how I define it. And this is something that I want us to avoid. So rather than presenting a cluster like this, for a ranked list on the right, I would present a description that's something like this. Age exactly 40, and income $150,000. Right? I mean, do you see that this is a better description? It's tighter. We call this tighter. rank. In order for me to define tightness formally, I need to first give you a little bit of a formalism, so please bear with me. And this formalism is based on two notions. It's the notions of a ranked interval and interval dominance. So what's a ranked interval? It's an interval. It's a one-dimensional thing. So an interval is age 25 to 30 or education and BA. But what makes it ranked is that I also, in addition to the description of an interval, I also store the top n items that fall within that interval. So do we remember what top n is? There was this ranking function that you can apply to any object. I get all the objects in the interval and I sort them and I get the top n. So what is interval dominance? It is what we call a rank-aware measure of locality that will allow us to explore the search space. And it's defined over two consecutive intervals, so intervals that are next to each other, over the same attribute. It's defined with respect to a fixed ranking function R, an integer n, and a dominance threshold. So there's a threshold, theta, there is a number between 0.5 and 1, and does not include 0.25. We say that interval I1 dominates interval I2 if the top n of the concatenated interval I1 and I2 contains mostly items from I1. And I'll show this to you. And by mostly, I say at least as many as the threshold specifies. So here's an example. I have two intervals, consecutive intervals over age. One, the red one, is age 20 to 24, and the blue is age 25 to 28. And the top n I'm showing here, pictorially they're the top n. Now if I concatenate the two intervals, that gives me 20 to 29. And let us now consider a ranking function, which I'll call R1, that just sorts on age in descending order. So from higher to lower, from ascending order, from lower to higher. So my ranking function again is on the same one attribute as the intervals are defined on. Right? So if I take the top 10 and even the top 20 of the concatenated interval, all of these items come from the red interval. They're all younger. Because my ranking function says younger is better. Do you see this? So in this case, what I have is that I1 dominates I2. I1 is better than I2. And I denote this by I2 less than I1. At top 10, up to threshold 1. So all of them, all of the top 10 are from the red interval. There are other situations also that are possible. So suppose that my ranking function is a little bit more complicated now. It's a weighted combination of income and education. And I'm going from higher to lower. So people who make more money and have a higher education level are better. In this case, over the same concatenated interval, I see that there are some matches that are red at the top end, but most of them are blue. This is because, again, higher age means higher income usually, but not always. So in this case, what holds, is that actually I2, the blue interval dominates I1 at top 10 up to threshold 0.8. And there's a final situation. This is my ranking function that says sort people according to how often they go to attend religious service, go to church or some other temple. In ascending order, from less to more frequent. And here what we see is that really for this interval here, 20 to 29, it doesn't matter if you are 25 or over 25. Your frequency of going to church is the same. So here neither interval dominates the other at top 10 for any threshold that is allowed. Okay, so I should fast forward a little bit. I think I'm going to put you to sleep. So how am I going to use this notion here of interval dominance? I will use it to help me ensure tightness. So this is our first property that I argued for. So suppose I have these two clusters. One says H35 through 39 education PhD. And in particular, I'm just looking at the top two items here, and I know that the age of one of them is 38, and of the other is 36. So they are this age bracket. They both have PhDs. And here I have an alternative description of the same cluster, so the same top two. Only now I'm saying that age is 30 to 39, education is PhD, and I'm ranking on income. And the question that I want to ask is which one of these clusters should I show? Or both to the user? Which one is tight? The left one is more tight for sure than the right. You see this, yes, right? And this is why. Because the left one at the top end, it has just apples. There are all these comparable people. They are in the age bracket that is tight and the same education level. On the right, I'm having trouble with this thing, sorry. On the right, what I have is that even though my top end is just apples, the description is apples and oranges. So this is bad for the user. He doesn't know what to find inside. So we don't want this. We want the one on the left. And how do we ensure that we get clusters that are like this, but not like that? This is going to be based on dominance. Why does this happen? This problem in the cluster on the right. It's because one age bracket dominates the other. 35 to 39 dominates 33 to 34 with respect to income compared to lower. Older ones are better with respect to income. And what that means is that I should not be concatenating in these two intervals together, because then everybody from the right bracket is going to be at the top. I don't want this situation. So what I want is if I detect that I1 dominates I2, then I only am going to use I1 and I2 separately when searching for clusters. If neither of them dominates the other, then I will use I1 and I2, and I will also use their concatenation, because that's going to give me an interesting mix of items that I can then use to detect correlations such as parallelism. So that's the basic conclusion. Basically, if you have dominance, don't concatenate. So what about choosing best from among comparable? This is easier to understand. Definitely. So the same ranking function income, and I have two clusters here that I'm showing. Age 33 to 40 in both of them. One has income $126,000 to $150,000 a year, and the other is 70 to 100. Is one of them better than the other? Given that user wants higher income? Yeah, so this one's better, and this I shouldn't show. Because this is a big apple and this is a small apple, but they are comparable. They're all apples. So what about this case now? I have age 33 to 40, income 125 to 150 versus age 26 to 30, income 75 to 110. Yeah, you cannot compare them. They're incomparable. So these are the apples and oranges. So I want to show both of them. this rank-aware clustering quality, this property, is going to give us this. It's going to allow us to remove these guys while keeping incomparable ones. I should fast forward here a little bit, but basically to define rank-aware clustering quality, what I need to do is define what are called ranked subspaces. So subspaces are combinations of multiple intervals that are interpreted as conjunction of predicates over my entire data set. So every item that is in a ranked subspace S, defined as age 25 to 30, education and BA, is going to meet both of these criteria. It's going to have both that education level and fall within the age bracket. And the dimensionality of a ranked subspace is just the number of intervals in it. So in this case, my subspace S has dimensionality 2. What I want is to find subspaces that have sufficient rank-aware clustering quality. What do I mean by that? I will be looking at the top n items in my ranked subspace, in my 2D subspace in this case. And I will be comparing these top n items to the top ends of the individual intervals that make that subspace. I'll show this to you. So suppose we have a ranking function again, income higher to lower, that we're looking for top 3 and times 3. It's just for simplicity, so I can show this to you pictorially. And that I have, sorry, I didn't tell you that this is with respect to quality threshold. We have a quality threshold, say the Q. That is going to tell us whether a subspace is good enough or not. So suppose that I have 2 ranked intervals that are over different attributes. One is over the age, and the other is over the education. And these are my matches just here. M1, 3, 7, 9, sorted on income in decreasing order. Here I have 1, 2, 3, 4. On income and decreasing order again. Okay? So the question that I'm asking is, should I put together these 2 intervals into a 2-dimensional ranked subspace? And it would look something like this: age 25 to 29 and education bachelor's, and the items that are in this subspace are exactly the intersection of the two, right? Still ranked on the same ranking function. What I observe here is that the items that made it into the intersection, M1 and M3, were there at the top end, top 3 of both of my constituent intervals. This means that when I combine them, I'm combining at the top. I'm taking the best from both. And in my 2D structure, I still have the best from both. And here, in particular, I have 2 out of 3, top 3 that I'm considering that are from the top ends of the constituent intervals. So yes, this is going to be a rank-aware subspace that is a cluster, where it has sufficient quality. Here's another case. I have older age, 30 to 34, different items, and I'm considering whether to now join this age bracket with this education. When I take the intersection and sort the items, I get at M2 and M4 in the intersection. M2 is among the top 3 of education bachelors. So it's one of the higher earners with this education level. But none of these items, M2 or M4, are there in the top 3 of the age 30 to 34. What this means basically is that I should not be putting together these 2 ranked intervals, and this is because intuitively people who are 30 to 34, the highest earners among them, have an education other than bachelor's, some masters and an MBA or PhD. So this is not a rank-aware cluster. These are not best from among comparable people, because there are other comparable ones with the same age that have a higher score and that are better. So this is the intuition really, and there are several clustering quality measures. The one that I just showed to you is based on just looking at intersections of sets and seeing what portion comes from the top end of the constituent quantity intervals. There are other variants where you can also incorporate the actual scores of the items, see sort of how high scoring the items are that are in the intersection. You can also incorporate the combination of score and right. So maybe you want to force that the intersection have to happen at the top of the top end. One technical detail is that because our algorithm is going bottom up, it's building 2D clusters out of 1D ones, then 3D out of 2D ones. It must terminate at some point. So these clustering quality measures have to exhibit what's called downward closure. They have to decrease, the value of clustering quality has to decrease as dimensionality increases. Otherwise, you just are going to explore your entire 30 or whatever dimensional space. That's not helpful. And we show that yes, these different measures exhibit downward closure. The final property, there are three. So there was this homogeneity that we didn't want, that tightness gave us. Rank over clustering quality I just discussed. And the final one is maximality. This is the easiest to describe. So basically, we don't want to produce redundant clusters that have slightly different descriptions but contain the same items actually at the top end. So here I'm giving you clusters, three clusters that are each combination of two different attributes: age, education, age, income, education. They contain the same items. Rather, what we want is to produce a 3D cluster here that has a slightly richer description and contains all of these same items. And this we will get for free just by using this bottom-up clustering procedure. And I won't say anything else about that. So this is just a brief recap of our algorithm. Tightness was ensured during merge, when we were exploring one-dimensional intervals. Maximality and rank over quality during join. I probably shouldn't discuss complexity of BARAC. Maybe skip this. But basically, it's that it's sharply complete, but in practice terminates much faster because correlations are low. Experiments. I'll just show you very briefly because I think this is the most interesting part actually. Here. So what happened here? We sat down, we talked to some users, we looked at the data. And we defined some completely new functionality. This is a new way of presenting results to users, the rank over clusters. How do we know whether this is any good? Is this just a cute idea, or is it actually useful for people? And to know this, you have to do user study. You have to take actual users of the system, show our results to them, and have also a control experiment where you show to the same types of users results that were possible with the previous approach, and see which one does better. So what we did was we ran a user study on a subset of paying Yahoo personal customers. This study ran over 5 weeks with the full dataset, fresh full dataset. We were using male users as guinea pigs, and they were searching for, so these were heterosexual males. They were searching for profiles of females. And the reason that we limited ourselves in this way is because we didn't want to accommodate both. And also men search for women more often than women search for men. So it was easier for us to get users on this way. 454 users, some 861 searches overall they executed. And we used a bunch of attributes, 19 attributes for the filtering, 17 for clustering, 6 ranking attributes to their work. And we used the simplest clustering quality measure. Our ranking function was just a weighted combination of the different ranking attributes that the users chose in the order in which they chose those. So if the user wants to rank by age higher to lower, this is going to be incorporated into our ranking function. If he wants us to rank by age from lower to higher, this is also possible. So we incorporate both which attributes he chooses and in which direction. And note that this ranking function is personalized because the user chooses which the components are. And these were the attributes, right, that we just saw. So how did we evaluate the effectiveness of our approach? We have to separate the effect of two components. One of them is what results we present, the content, and the other is how do we present the presentation. So presentation, there are two ways to do it. You can present a list of results. This is how results are usually presented as a ranked list. Or you can present them in groups with descriptions. As far as content, there are two ways in which we can get the matches. Right? We can look maybe at the top 100 according to the ranking function. Or we can get results from the clusters. So we can let our algorithm run, get 10 clusters, and then take 10 results from each. And this is going to give us another set of results. So this set is going to be more diverse. It will contain matches from different parts of the ranking. But overall it will have lower quality. So if ranking is by income, some matches will have lower income than was possible.
Is it possible for user to choose a cluster after the results are ready, or he can just see the list?
Yes.
Attributes should use the user for the best result.
This is up to the user. So the user knows what their preferences are. And this is not working again. So basically, let me show you what I can on this slide, and then I'll go back. We separated users. So we randomly, whenever we have a user who wants to participate, we randomly assign him to one of 4 groups. And we compared how many things users liked by group. So in one of the groups, the users had no choice whatsoever. Or rather, I should say, so the user always specifies the filtering conditions. So they always say, I want a certain age, certain income, whatever. They always also specify the set of ranking attributes from among 6 that there are. There are only 6 on which there is any order in Yahoo Personal, so these were the only ones we could use. The user could specify between 1 and 6. We don't tell him how many to choose or which ones. He knows whether income is important to him or not, whether height is important to him or not. This is not up to the system. What is up to us is to allow him to see diverse results somehow from among those that are returned and ranked. So all users just choose these filtering conditions and they choose a ranking function. Depending on which group they were placed into randomly, they will either see a top list, so this is just a traditional 100 results ranked on the user's ranking function. We show them 10 to a page, so you see 10, then next, 10, next. I'll show you this. BARAC list has the same interface, so it's also 100 results that you see, 10 to a page. But these results are not the actual global top 100. They are a combination of top 10 results from 10 groups that we compute, 10 BARAC groups. And then 2 other alternatives was top groups. Top groups is a very sort of down way to do this. It's user sees results in groups and clusters that are described, but they're described by top 1s with 10, top 11s with 20. So that's the top groups result. And then BARAC groups
It's the
is,
same as the top list,
but it's just that they're labeled. So if he wants, he can very easily fast forward to top 30 people, and nobody would actually use this in the normal system. The only realistic ones really are these three: top list, BARAC list, and BARAC groups. So BARAC groups is sort of the full power of our algorithm. But we had this just for completeness.
Work.
Yes. So this is what the top groups and top lists looks like. Actually, it was slightly different. It wasn't 100 women. It was 10 women, and then you go next. So these are just profiles of these people. And this is a BARAC groups. I don't know how well you can see this, but basically there are two